In this statistics lesson, we will be discussing how to find confidence intervals for the mean if you do not know the standard deviation of the population. If we don't know the standard deviation of the population, the first thing we have to do is we cannot use our z distribution. Okay, that's not possible anymore. So we have to use a t distribution. T-distributions are approximately normally distributed, but not quite. And instead of using a critical value of z sub c, we would use a critical value of t sub z, indicating that we used a t-distribution rather than a z-distribution. And just a fun fact, this whole distribution was actually created by a man who worked for the Guinness Brewing Company. His pen name was Student, which is why sometimes you will hear this t-distribution called the student distribution as well. So let's talk a little bit about the t-distribution, what it looks like, its properties, and then we can start using it. All right, so in the t-distribution, the mean, the median, the mode are 0, just like they are in the z-distribution. The t-distribution is bell-shaped and symmetric about the mean, just like the z-distribution. The total area under the t-curve is 1, just like the z-distribution. The tails, however, in the t-distribution are thicker than those in the z-distribution, that standard normal distribution. And the standard deviation of the t-distribution varies with sample size, but it is greater than 1. So just know that your standard deviation will be greater than 1. The last property is that the t-distribution is actually a family of curves. And each curve depends on what we call the degrees of freedom. Now, degrees of freedom is just the sample size minus 1, so it's not a difficult thing to find. Once you have found your degrees of freedom, then you can look to see which curve belongs to you. So let me kind of give you a breakdown of what these curves look like in property number 7. All right, so in this picture, the blue curve is our standard normal z distribution, right? Notice as our degrees of freedom get smaller, the curve gets closer and closer to the curve in blue. So if you only have 2 degrees of freedom, which means a sample size of 3, we're in the black. And notice the black is the tail is much fatter here, and that it's much lower than the peak. But if I move up to degrees of freedom of 5, which would be a sample size of 6, the tail is getting much closer and the peak is getting much closer to the standard normal curve. So as the number of degrees of freedom increases, it's going to get closer and closer and closer to looking like that standard normal curve. So you will see that a lot of things that we do behave exactly like the z distributions do. It's just we have to use a slightly different chart, and that will be provided to you as well. All right, so first thing we have to do is we have to find critical values, find those t sub c's. So just like we would do with the z, we are looking for a 95% confidence and a sample size of 15. So our n is 15, which means that we are going to use degrees of freedom of 14. Okay, so the z chart looks slightly different. So let me show you what it looks like. So here is what the t chart looks like. So you're going to go over here to 95, because that is our level of confidence. And then you're going to go down until you get to 14 degrees of freedom. And where there's those two, that column and that row cross, that is going to be your critical value. So 2.145. And then here is kind of the breakdown. Again, that curve looks very similar. We're going to have 95% in the middle, and then there are our critical values on either end. So it looks very similar to the z as well. It's just that those critical values are going to come from this chart. So I'd go back up here, and my t sub c is equal to 2.145. Again, so make sure you know how to use the chart, and that will help you a lot. All right, and the steps are very, very similar to finding the confidence intervals. The only difference is that we'll have to use S. So we'll use X bar, and we will also have to calculate S for each problem if it's not given to us. All right, so if you randomly select 16 coffee shops and measure the temperature of the coffee sold, so our N is equal to 16. So I'm going to write down all the pertinent information as I read along. The sample mean, so the X bar, is 162.0 degrees Fahrenheit with a sample standard deviation, nice of this, they gave us S, of 10.0 degrees. They want us to construct a 95% confidence, so our C is 0.95. A confidence interval for the population mean of the coffee sold. Assume the temperatures are normally distributed. So because we don't have sigma, that tells us we have the S instead. That means we're going to have to use that T distribution. Okay, so we need to find our T sub C of 95%. So we're going to go to our chart. We're going to go to 95% level of confidence, and we're going to go down to 15 degrees of freedom. So you need to make sure that your degrees of freedom is 15, right? It's one less than the sample size. So 15, and then I go over to 95%, and where that row and that column cross is 2.131. So there is your critical value for this problem. So my margin of error is going to be that critical value from the T times S over the square root of N. So notice how similar that was to what we did before when we did the Z's. So I'm going to plug in all that information. So 2.131 times the standard deviation over the square root of 16. Again, make sure this is the square root of N. Very common mistake is that people put the degrees of freedom here instead of the sample size. So make sure you just pay attention to that. So put that on my calculator, and that turns out to be approximately 5.3 degrees Fahrenheit. So my error is, my margins are exactly the way they used to be, right? We're just going to take the mean, the population mean is somewhere between the X bar, which was 162.0, minus that error, and then the high end would be 162.0 plus that error. So that gives me 156.7 and 167.3. So I am 95% confident that the mean temperature of the coffee is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. So you'll notice it's very similar to what we were doing before with the Z's. Not much difference. All right, so if you would like to try one, go ahead and press pause and then give this one a try. All right, so first step I'm going to do is I'm going to go through and I'm going to read and find all the important problems. So the first thing I see is that N is equal to 36. I see that the sample mean, so the X bar, is 9.75. A sample standard deviation, so my S is 2.39. My C is 0.99. And then I can look up my critical value for that 99%. So I'm going to go to my 99% column. I'm going to go down to 35 degrees of freedom, right? One less than the sample size. So where those two cross is 2.724. Right? And then I'm going to use that information to plug in to find my error. All right, so the 2.724, I'm going to multiply that by my S, which was 2.39, and divide by the square root of 36. Again, make sure it's N, not your degrees of freedom. Okay, so the error would approximately be 1.09 days. So there's my margin of error, and then I would set up my interval. So I'm going to do my X bar minus that E on the low end, and then on the high end, I'm going to do X bar plus that E. So 9.75 minus 1.09, and then 9.75 plus 1.09. So my low end is going to be 8.66, and my high end is going to be 10.84. So I am 99% confident that the population mean number of days that the car sits on the dealership's lot is between 8.66 and 10.84 days. All right, so the only question then becomes, how do you know when to use a normal and when to use a T? Like how do I know? So if the population is normally distributed, so if they tell you it's normally distributed, then yes, you go down this direction. If it's no, then or the sample size. So if it's either of those don't apply, then you can't use either. So luckily for you guys, we're not going to give you any trick questions like that in my class. So the answer to one of these two is always going to be yes. And then you just ask yourself, is your sigma known? If it is, then you use your Z. If it is not, then you use your T. Very straightforward. All right, so it's not complicated. So let's test and see if you can figure this out. All right, so you randomly select 25 newly constructed homes. The sample mean construction cost is $299,000 and the population standard deviation is 46,000. Assuming construction costs are normally distributed, should you use the normal, the T, or neither to construct this 95% confidence interval? So first question you have to ask yourself from that flow chart is it normally distributed, or is your n greater than or equal to 30? And they told you right here that it is normally distributed. Told you this right here. Costs are normally distributed. So that is good. I've met my first qualification. Then you have to ask yourself, is your sigma known? Do they give you the population standard deviation? And they did. It is right here. Population standard deviation. There is your sigma. So because that means you will use the Z, right? You will use the standard normal. Distribution for this problem. All right, let's try another one. So feel free to press pause and then walk through it. All right, so first question you have to ask yourself, is the population normally distributed? So we're going to look in the problem for that. It says right here, assuming the heart rates are normally distributed. Okay, perfect. So we have that qualification, so we're good. Is sigma known? So we're going to go look and see if it gives us the population standard deviation, which it does not. Notice here it says it gives us the sample standard deviation. So sigma is unknown. And because sigma is unknown, that means we have to use the T distribution. So it's all about making sure that you are reading through the problem and picking out the correct information that you need. So hopefully that helps you out. Come back next time when we'll start doing some intervals for proportions instead of means. See you then.